By the end of this video, you'll have an intuition for what voltage, capacity, and energy mean with respect to batteries. Plus, I'll also be quizzing you along the way to get you ready for your next test, job interview, or just general knowledge you want to share at parties. Anyway, let's get started. To build intuition for voltage, let's look at this analogy. Say I want to move this ball from the left to the right. We know the ball won't move on its own, and that's because the change in height is zero. Once we tilt the plank, the drop in height is greater than zero, and the ball will roll from high to low. Now let's talk about voltage. Here is a copper wire by itself. I'm going to connect it to a light bulb so that the electrons can flow through it and light it up. However, the electrons will not flow through the light bulb just because I asked. This is the same as the plank being flat and the ball not rolling. Instead of creating a height drop for the ball to roll down, I need to create a voltage drop for the electrons to move through the light bulb. And this is what batteries do. So I created some space to put a AA battery. And if you look at the AA batteries that you own at home, you'll see that they say 1.5 V. That's saying that the voltage difference from the negative to the positive is 1.5 volts. As for the ball analogy, this is like saying the height difference is 1.5 meters to the ground. Watch what happens when I connect the battery to the circuit. Instantly, the voltage drop is created in the circuit, which means electrons will flow through the light bulb and light it up. Electrons will flow from the negative terminal to the positive terminal. But we all know batteries die eventually, which means the voltage has to decrease as the battery is used up. To understand how voltage decreases as the battery is used up, we need to look at voltage versus capacity curves. We just went over voltage at a superficial level, and we'll delve deeper in future videos, but this is good enough for now. Now that you have an intuition for the y-axis, let's build one for the x-axis, capacity. You may have heard of these smartphones, but not many people look at the battery specs. Here we can see that the Galaxy S24 Ultra battery has a greater capacity by about 500 milliamp hours, mAh. So what does that mean? More importantly, what is a milliamp hour? Milli is just a unit of scale, meaning 1/1000th of a unit, like millimeter or milliliter. Let's remove it for simplicity and focus on the rest of the word. Amp is short for ampere, named after some French guy, but basically an ampere is a unit of electric current, or how much electric charge is moving per unit of time. But I like to think about it as how fast electrons are passing on average. You can use an ammeter, which is a device you put in your circuit to measure the flow of electrons in amperes. So where does hour come from, and how does this relate to capacity in amp hours? Let's break it down. 1 amp is defined as 1 coulomb per second, and 1 coulomb is a bajillion electrons. Therefore, an amp is just a bunch of electrons passing per second. And when we say amp hour, we are just multiplying it by an hour. And an hour is 3,600 seconds. When we multiply them together, the seconds cancel out. Therefore, an amp hour is just this many electrons. More importantly, an amp hour is a unit of charge. You can think of charge in electrons, coulombs, or amp hours. So why don't we just use coulombs then? Since the Galaxy S24 battery has 5,000 milliamp hours, and 1 milliamp hour is 3.6 coulombs based on my calculations from before, we can say that the Galaxy S24 has 18,000 coulombs of capacity. But here's why we use amp hours in the battery world. Say your phone is doing an activity that requires 100 milliamps, like turning the flashlight on. If the battery was only doing that, it would last 50 hours. How do I know that? I know that because 100 milliamps times 50 hours equals 5,000 milliamp hour, which is all the capacity the battery can hold. So if I asked you how much would the battery last if it was discharging at 500 milliamps of current, you can divide the capacity by the current to get hours. Milliamp hour divided by milliamps cancels out the milliamp, and you're left with hours. In this case, it will be 10 hours. And if the battery is discharging at 1,000 milliamps, it will last 5 hours, and so on. For any current, you can predict how long the battery will last for. This is for an ideal battery, by the way, and in future videos, we'll go over which conditions this relationship breaks down. But the important thing to take away is that this is why we prefer to use amp hours for capacity instead of coulombs. It's easier to discuss the phone battery when you tell me the capacity in amp hour instead of coulombs. And definitely please do not tell me how many electrons your phone can discharge. And that's pretty much it for capacity. Now you're ready to combine what you learned about voltage with what we just learned about capacity. One thing you'll be able to do now is check the battery health. But before we do that, we're going to be looking at a lot of voltage capacity curves, so it's best we get familiar on how to read them. When I first saw these, I wish they labeled the x-axis completely. So let me do that for you. The x-axis for this graph is capacity discharged. Here we are looking at a AA battery voltage capacity profile as it is discharged at a constant current of 100 milliamps. To understand any plot, I always like to look at the extremes. In this case, let's look at when capacity discharged is 0, which means no amp hours of capacity has been discharged by the battery. If nothing has been discharged, then your battery is at 100% state of charge. And when Y is 0, the voltage is 0, so there is no force to push electrons through the circuit. You may call this battery dead. For this AA battery, it can't do any more work after 0.6 volts, so the plot ends there. Okay, so now that we know that, how can we use this to determine how many hours the AA battery lasted? We know that when the voltage of the battery is 0.6 volts, it cannot push electrons anymore and is considered a dead battery. When the voltage is 0.6 volts, the battery was able to discharge 1.65 amp hours of capacity. Since the constant current was 100 milliamps, then we have everything we need to know to figure out how long it lasted for. Amp hour means amps times hour. If we rearrange the equation to solve for hours, then hours equals amp hour over amps, or capacity over current. We know the discharge capacity was 1.65 amp hour and the current was 100 milliamps. I'm going to convert 100 milliamps to amps so that the units are consistent and cancel out. When we do that, we get 1.65 amp hour divided by 0.1 amp, which is 16.5 hours. Feel free to rewind this part if it wasn't clear. If you understood it, ready to try on your own? My fully charged 5 amp hour phone battery lasts me 10 hours for the day. How much current am I pulling from it on average? 50 amps, 2 amps, 0.5 amps, or 0.2 amps. Pause the video if you need more time. If you said C, 0.5 amps, you're correct. The fully charged battery capacity is 5 amp hours. It lasted 10 hours to fully drain it. We want to know the current. In real life, our phones don't discharge at constant current the whole time, which is why I said on average. To solve for current, I divide the capacity in amp hour by the time in hours to cancel out the hours, and be left with amps, which is the unit of current. 5 divided by 10 is 0.5. So the answer is C, 0.5 amps. If you didn't get C, that's okay. You can always rewatch some parts until you understand why it is C. Now back to the curve. I said you can check the battery health, but I only talked about a fully charged cell and a dead one. I think we all know how to tell those apart. What's more interesting is knowing when a battery is at 50% or some other percentage in between. Let's use 50% as an easy example. Notice how I didn't write 50% at the halfway point of the y-axis, but instead I wrote it on the x-axis, where capacity is. State of charge, or SOC for short, is equal to the capacity left over divided by the fully charged capacity. So if this AA battery had 1.65 amp hour of capacity at fully charged, then 50% is half of that, which is why I drew this line at 0.82 amp hour. To approximate how much is left in the battery, there is no such thing as a capacity reader that I can measure by touching the cell, but there is a voltmeter which can touch the terminals on the cell and read a voltage, and we can use that voltage to see where we are on terms of capacity. In this case, 1.15 volts maps to about 50% capacity. Okay, and now let's talk about energy. Energy is the universe's currency, meaning if you want something done, you need energy to power that. So how do batteries give us energy to make things work? Energy standard unit is joules, named after some English guy. Capacity is in units of amp hour or coulombs, and voltage is in units of joules per coulomb. And I know, I'm sorry for keeping that from you for this long, but I wanted to introduce voltage with the height analogy, and I didn't want units to get in the way. Anyway, from these units, we can see that if we multiply capacity and voltage, we get energy, since coulombs cancel out and we're left with joules. Okay, so energy equals capacity times voltage, which is similar to how the area of a rectangle equals the length times the width. Going back to voltage capacity curve, if I want to know the energy that the battery discharged instead of just the capacity, I would have to take the area underneath the curve. You'll need calculus for that, but most battery testing software already has tools for that. You may be wondering, if I'm multiplying capacity times voltage, but I said that we use amp hours for capacity instead of coulombs, how will that get me to joules? Well, it won't, but it will get you to watt hours. Well, what is a watt? I always like to say, what is the unit of power? What is the unit of power? You already know the drill. Watt, the unit of power, is named after some Scottish guy, and power is how much energy you can deliver per unit of time, or joules per second. This means 1 watt is 1 joule per second. A watt hour is just 1 watt times 1 hour. An hour is 3,600 seconds, therefore a watt hour is 3,600 joules. And with that being said, are you ready for the last question? The vertical orange line showed 50% capacity leftover. Where would the 50% energy leftover line be located? To the left of the orange line? The right? It wouldn't change? Or is there not enough information to answer this question? Pause if you need more time. If you said A, to the left of the orange line, you are correct. If I had to eyeball it, I would put the 50% energy leftover line about here. When it comes to energy, we have to look at the area underneath the curve, and since the voltage is higher on the left side, we don't need to travel that far from the left to the right to get 50% of the area. Here's my best attempt at drawing the area underneath the curve of the left side. Hopefully you can see that this area and the area to the right are about the same, 50-50. If I split it by 50% capacity, you can see that there will be more area on the left side. The main takeaway here is that 50% state of charge is not the same as 50% state of energy. This is very important, and make sure you understand this before moving on to the next video, or else it will be more confusing to learn future topics. But if you understood all of this video, congratulations! You are ready for the next video, where we will discuss how a lithium-ion battery works.